we're going to finish up our Kinetics 2 experiment, determining the activation energy and the effect of a catalyst on this iodine clock reaction that we've used for 2 weeks now. If we plot ln of k on the y-axis and 1 over t on the x-axis, then we're going to get a line y equals mx plus b, where the slope is equal to negative activation energy over R. R, of course, is 8.314 times 10 to the minus third, because we're in kilojoules per mole K. Okay, so this is the point of this lab. We're going to measure the time it takes for a reaction to turn blue, to react, the iodine to react with the starch to turn blue. And we're going to measure that time and we're going to measure the temperature. And using the time, we're going to be able to find the K. And obviously, using the temperature in degrees Celsius, it's not too hard to get 1 over temperature in Kelvin. So this is the same equations, the same reaction that we did last week. And what we ended up with finding out last week was the X and the Y, the exponents or the orders of reaction for this particular rate law. And I think the vast majority of you found that each of these, the X and the Y, are both 1. Okay, that's a 2 minus. So this particular reaction was first order with respect to persulfate and first order with respect to iodide, second order overall. So this particular reaction now, if we rearrange it, we can get a reaction, equation that we're going to be using all day today, which is using the rate to find the K. Okay? Now, as you did this week's experiment, you probably noticed that these concentrations stayed the same. You always had the same concentration of persulfate and the same concentration of iodide. So that was kind of nice because you could multiply it out once and then just use it the rest of the day. And that was pretty cool, or will be pretty cool. Makes one less calculation. Okay, so this is going to be a constant. We're going to gather our data and a few equations that are really important for us to have, and we're going to do this thing. Now, this is table 2, and it's figuring out the data and calculations for an uncatalyzed reaction. I highlighted in green here what the data was you actually took, and that was it. Now, I'm going to do one example for each temperature, and you can see I've already done that out because we need to do some data manipulation before we can do anything about finding a curve or a graph and finding the activation energy. So first of all, I need to take the reaction temperature from degrees C to degrees K, and that's just adding 273.15 to it, which is what we did. And it's what I did in every single case here. The next thing we needed to do was take the reciprocal of this. So 1 over 283.15 gave me 0.00353. Okay, so that filled in the next column. So now you're all done with the temperature part. We now are going to have right here the x coordinates. So now we have to find the y coordinates. Remember, this is 1 over temperature in Kelvin, but the y coordinates are ln of k. So all we have right now is a time. So remember, the rate we found the exact same way we found it last week, which is that rate is equal to the change in iodine. Remember, this is a rate of appearance, the change in iodine over the change in time. Now we have all the times, but what we had to do was find this delta I. And we do it the exact same way we did it last week. Remember that you had to use up all thiosulfate before we could actually detect the presence of iodine. So this is exactly the same equation that we used last week, with the exception that instead of 11 milliliters total, like last week, it's 13 milliliters as your final volume, which gives you 0.000923. And just like you used your delta I to every calculation last time, we're going to use it every calculation this time. So now we have found our delta I. And we actually wrote it in right there, 0.000923. Now my rate is that delta I divided by change in time. So rate, and I'm going to use this data right here, rate equals the change in iodine, 0.000923, divided by the time, which was 260 seconds. So this rate ends up being 3.55 times 10 to the minus 6th, which is exactly what I wrote here. Now again, I did this over and over and over again. 0.000923 divided by 252, etc. The ones I'm showing you is 0.00923 divided by 160 seconds now, which gave us 5.77 times 10 to the negative 6th. All right, so now, given that we have found our rates for the 4 different temperatures, so how do I get from rate to K? Well, that's a good question. So let's go back to that set of equations that I put on this page initially and see if we can find something. There it is. K equals rate divided by the concentration of the 2 reactants. Use table 1, the data from table 1, in order to figure out these concentrations. S2O8, 2 minus, equals, let's see, we took 2 milliliters of it. I'm looking at the top part, not at the making the test tubes, times 0.200 molar, ran out of room there. That's what the concentration of persulfate was, divided by the total number of milliliters, which was 13.00 milliliters. Now my milliliters cancel, and this does in fact give me 0.0308 molar. So that went in right here. And I did the same thing again for iodide using its number of milliliters, its concentration, and the total of 13. Okay, so now once I've gotten these 2 concentrations, I can multiply them together and use it in every calculation. So that's what I did. And I got the product of their concentrations was 0.00189. Okay, so we're looking for K. K equals, what's the rate? 3.55 times 10 to the minus 6 divided by the concentration of persulfate times iodide, which was 0.00189. And making sure that I used my exponents correctly, I did end up with 0.00187 as my K for that very first run. Now, right away, I just took this number, typed in ln or pressed the ln button, and then put 00187 in. And lo and behold, there was my ln of K, negative 6.28. If you run into difficulty, well, first you should always try to figure it out. But then if you can't get it figured out, let me know and I can help you. All right, so that's it for the uncatalyzed data. We are going to plot this. I'm trying to remember to do that. And if we look here at the catalyzed, we've done the exact same thing. So now what I did was go to LoggerPro, and there are extensive discussions throughout right here on page probably -8 about how to use LoggerPro for this, and I would recommend you do. So when I was done using LoggerPro, I had an uncatalyzed set of data, and I had a catalyzed set of data. And because I had these both in the same data table using data set 1 and data set 2, I could put them both on the same graph. So I was able to compare my catalyzed versus my uncatalyzed. My catalyzed is here on the top. My uncatalyzed is here on the bottom. And you can see the catalyzed has a less steep slope. Well, what does that mean? Now we go back to Arrhenius. ln of K equals negative EA over R times 1 over T plus ln of A. Y equals mx plus b. So my slope is equal to negative EA over R. So let's do this for catalyzed. We'll go to red for catalyzed. I have negative EA over 8.314 times 10 to the minus 3rd kilojoules per mole K equals, let's see, negative 4651. Okay, so obviously I'm going to cross multiply. So this ends up being negative 4651 times 8.314 times 10 to the minus 3rd kilojoules per mole K. And that cancels this out. I found my activation energy to be, first of all, those negatives canceled, didn't they? EA equaled 38.7 kilojoules per mole. That should just be kilojoules per mole because this slope's units are actually 1 over Kelvin. So now we're going to go on to our uncatalyzed. And do you remember what a catalyst is supposed to do? Right, a catalyst is supposed to lower the activation energy. So we'll see if this is lower than your uncatalyzed or not. So let's see, I have negative EA over R equals slope. So EA equals negative MR. And this activation energy is 50.2 kilojoules per mole. Well, there you have it. Now we have our activation energies. And in fact, the uncatalyzed activation energy is quite a bit bigger than the catalyzed. It wants us to find A. ln of A is the y-intercept, right? Right here. So for catalyzed, ln of A equals 11.06, which means A is equal to E to the 11.06, or 63,600. No units. So now let's try the uncatalyzed. Again, ln of A is equal to, uncatalyzed, way down here, 14.99. So A equals E to the 14.99, or A equals 3.24 times 10 to the 6th. It's a whole lot bigger than this one. This was 6.36 times 10 to the 4th. Okay, gone way, way up. You find your quality of data, your correlation from this point on the graph right here. It says 0.9942 and up here 0.9904. So I have the graph that you have to include. And finally, the questions. This is exactly what you did last week. So just go ahead and do it the same way. Next question. When you looked at your data, which reaction has the higher activation energy? We just talked about this. Is this what you would expect? Why or why not? Again, if you can't remember it, back the video up about 5 minutes and we talked about this. A is the frequency factor. Now, I'm not going to tell you what that means. You need to go back and look in your notes or Google it. Tell me what the frequency factor represents in the collision model in kinetics and why it's important. And you'll be done.